Alright, in the last video for week 5 is going to discuss acceleration. Just as an opening problem, if we think of an object in elliptical motion, its position, so that's the x of t is its position at time t is given by that. We want to find expressions for its velocity and acceleration. So I encourage you to just pause the video here and take a shot at finding the velocity and acceleration vectors. All right, and just to check your answers, what we should have got, so if I have velocity at time t, that is going to be, let's see, negative a omega sine omega t, comma, and that should, actually this should have been b, I made a typo there, that should have been b omega cosine omega t. Okay, and I should put parentheses around there and there. All right, and then a of t is, and just, so v of t was the derivative of x of t, and so a of t is just the derivative of velocity. So I should get minus a omega squared cosine of omega t, comma, minus b omega squared sine of omega t. Okay, and that's all we have. Just as we look at this a little bit, if we had omega equal to 1, then what I get is that a of t is, as a vector, is the opposite of x of t. And the second observation here is that if I have a is equal to b, then we actually notice that a is perpendicular to v, and I'll just say you can check that by doing a dot product. Okay, so that's kind of fun. But now I want to go back and look at how these things relate to t, n, and b. Okay, and so we might remember that t, okay, we might know this definition by now, is the derivative of vector x over the length of that derivative of vector x. Okay, well, as we said above, right, x of t derivative is just the velocity vector. Okay, so another way of thinking of the unit tangent vector is it's just the velocity vector over the length of the velocity vector, also known as the speed. Okay, so again, this part down here we think of as speed. Okay, and well, if I just rearrange it and solve for v, okay, what I end up getting is that v is equal to the length of vector v, or the speed, times the unit tangent vector. Okay, well, that's kind of fun. Okay, so that might be something that we keep in the back of our brain. Okay, another thing I can do is, well, let's look at the unit normal vector. Okay, well, we said that was the derivative of the unit tangent vector over the length of the derivative of the unit tangent vector. Okay, this is a lot to say all the time. Okay, and so what I can do with this again is just rearrange, solve for that a little bit. Okay, and I get the derivative of the unit tangent vector is equal to the length of the derivative of the unit tangent vector times that unit normal vector. Okay, and now I'm going to do something that's not completely obvious, but I can actually say, okay, the unit tangent vector derivative is equal to, let's see here, so we're going to have kappa times s prime times the unit normal vector. Okay, and where this came from was remembering that curvature is the same as the length of the unit tangent vector derivative over ds. Okay, so it was dt over ds, where s is still that s is that arc length function. Okay, not to be confused with position, because sometimes we use s of t for position. Okay, so that's where that little bit came from. Okay, going just a step further. So I have the derivative of the unit tangent vector, and I had an expression for velocity up above. I'm kind of curious about acceleration, right? Well, I said that acceleration in our first example was the derivative of velocity, and that's certainly true. So if I take that expression for velocity, so it was the length of the velocity vector or speed. We can also call that the arc length function, the derivative of the arc length function here, times the unit tangent vector. Okay, and so I take the derivative, the time derivative of that. Well, by definition, this is going to be s double prime times the unit tangent vector plus, and then doing chain rule here, it would be s prime vector t prime. Okay, and so then just plugging in what I know, this is s double prime t prime plus, and then I'm going to substitute in for vector t prime, and what I end up getting is plus s prime quantity squared, because I have s prime here and one s prime from there, times kappa times the normal vector. Okay, and this is really nice because what this does is it takes the acceleration, so this is the acceleration vector yet, and breaks it down into a tangential component. Okay, tangent component, and a normal component. And this is really helpful when working with physics, because tangent component is at a point, if it were to continue in straight line motion, that's what it would happen. But if we do have some curvature in here, that the second component, the normal component, is going to account for any curvature in our path. Okay, so with that breakdown, there are a couple things that we need to note. First thing is that the vector A, our acceleration vector, is a linear combination of t and n. Okay, and as a result of it being a combination of t and n, this acceleration vector is in the osculating plane. Okay, because again, t and n create that oscillating plane. Okay. Let's see. Thirdly, we have if so this s prime squared, that's certainly always greater than 0, square, right? And we also have that curvature is greater than or equal to 0. These two ideas together tell us that A, the acceleration vector, points in the direction we're turning. Direction we are turning. Okay. Fourthly, if kappa is equal to 0, so if we have no curvature, right, then we have no normal component, and then therefore our acceleration vector is just parallel to our tangential, or our unit tangent vector, or the tangential component. Similarly, if speed is constant, okay, then that means, that the second derivative of our arc length function is 0, and then therefore we have no tangential component, so we have a acceleration vector that is parallel to the normal vector. Okay, this is most commonly associated with circular motion. Okay, and then just as a caution, something to be mindful of is that we can have constant speed and non-zero acceleration. Okay, in a physical sense, this would be whenever you have circular motion going on, so you might have a parameterization along the line of like cosine t, sine t, to reflect that it's going in a circle. Okay, and that's it for week 5 videos. We'll plan on seeing you on Wednesday. Enjoy your weeks until then.